Good day, I'm Maile Matsiba. Welcome back to our channel. Today we continue with our semester test 2. We're looking at part 2 of semester test 2 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. So in the first part, we looked at this question and we did question A and B. So in this part, we're going to be looking at C, D, E, and F. So now looking at question number C, we see they say that calculate the recycled stream R flow rate in kilomole per hour. So what happened initially is that, this is recycled stream R. In the first question, in B rather, of the same question, we're told that we should calculate the percentage composition, or rather the mole fraction of methanol in the recycled stream R. And we did that, we're able to find that. Now, they want to know the total flow rate of stream R in kilomole per hour. So if we're going to do that, there's a couple of ways to do it, and an easier way would be to create equations. And the first equation that we're going to be doing is we're going to do a mole balance around the mixer. It's easier here because we already know F, and then we have some details of A, so it's gonna be easier. So the first thing we can do, we can just make let me just write down that total mole balance at the mixer is the total mole balance at the mixer, right? This is the mixer here. So the first equation is that we already know from the diagram that F plus R is equals to A. So we can just simply say that F plus R is equals to A. So this becomes our first equation, right? So now that we have our first equation, by making the total mole balance around the mixer, we can actually, because we have three unknowns, we need three equations. So the second equation that we're going to be looking at is we're going to do a methanol, which is the CH3OH balance around the mixer again. The thing is, we have the composition of the methanol here. We have been told from the problem statement that the fresh stream entering F is actually 4% methanol. So we already have the mole basis, or the mole fraction of methanol in F. And also in A, we are told that the methanol is actually 16%, right? So we also have like the mole fraction of methanol in A. Now in R, we did calculate the total analysis of stream R percent-wise and also in moles. So we know the mole fraction of methanol here. So it would be easier for us to use that to get the second equation. So we can just say methanol balance at the mixer, right? So we know that this is the methanol balance at the mixer. We know that there's 4% methanol in stream F, so we can just simply say 0.04 F, right, plus, now checking the methanol in R, according to our calculations, we discovered that there's actually 17.4672% of methanol in R. You can check the first part of this question. We did calculate it there. So we already now know that 0.174672R, right? This now is the methanol, because 17.4672 for mole fraction is going to be 0.174672. So now we find the amount of methanol in R is equals to, now again going to the problem statement, we are told that in stream A contains 16% methanol, so we can just say it's equals to 0.16 A, right? Then this becomes our second equation. So with that said, we have two equations, but we have three unknowns, or I can call them unknowns. So, but now we are told here that you need to use a basis of 100 kilomole per hour fresh feed F to calculate the following, right? Which are the questions that I'm talking about A and B and now C. So which means for our third equation, we can simply say F, which is the fresh feed stream, is equals to 100 kilomole per hour, and then this becomes our third equation. So we have three equations and three unknowns. So doing the calculations, which is the mathematics part of it, so we can just simply say, therefore, let's say 100. Okay, so let's say let's substitute 3 in 1. So let me just say substitute 3 in 1, right? Remember that now we are doing the mathematics, we are done with the chemical engineering, so we simply doing the arithmetic just to make sure that we solve for the unknowns. So substituting this one in here, we're going to be having 100 plus R is equals to A, right? So that becomes our fourth equation. Now with that said, if we have this as the fourth equation, we can move further to go to equation to go to the second equation. Remember, in the second equation, there's also F there. Where is F? Yeah, there's also F. So we can just say substitute 3 in 2. So here I'm just simplifying the equation so that I can eventually be left with two equations and two unknowns. So with that said, if we take 100 kilomole and substitute it there, we have 0.04 multiplied by 100, right, plus 0.174672 R is equals to 0.16A, right? So this becomes 4 plus 0.174672 R is equals to 0.16A. Then this becomes our fifth equation. So with this said, if we get to the fifth equation, we can then continue further doing the mathematics and substitute 4 in 5. Let me just write it down here, that substitute 4 in 5. So if we substitute 4 in 5, remember A is equals to 100 plus R, so we can just take the 100 plus R and substitute it here and say, therefore 4 plus 0.174672 R, right, is equals to 0.16. Now in A we put 100 plus R, right? So doing the simplification, we can be left with 4 plus 0.174672 R is equals to 16 plus 0.16 R. And now as you move further, it gives you, because now remember we only have one unknown now, which is R, so we can just take everything in one side. We'll be left with 0.174672 R minus 0.16 R is equals to 16 minus 4, right? And with that said, you have 0.014672 R is equals to 12, right? Therefore, R is equals to 12 all over 0.014672, right? Is it still visible? Yeah. Therefore, R is equals to 817.8844 kilomole per hour. So yeah, this then concludes C, which was saying calculate the recycled stream R flow rate in kilomole per hour. So this is the answer of recycled stream R. It's 817.8844 kilomole per hour. So thank you for your time, and I hope we meet again in our next video.